Hi students, all of you welcome. Welcome to Sunil Engineering Academy. Students, in this electrical machine transformers, we have already completed 4 sessions now. It is the fifth one. And students, if you have not watched the previous session, click on playlist and you can find out the previous session. Okay. And anyone want to get the PDF, you can visit sunilengineeringacademy.com and you can get the PDF. Okay. Yes. So I said earlier, in this fifth session, we are going to learn about transformer losses. Very, very important topic. So losses in the transformer. Okay. And students, if you still not subscribe this channel, please click on subscribe button and also please share to all your friends. Yes. So losses in transformer. We know very well about the losses in any machines. So the major losses may be, one is the copper loss, second one is the iron losses. Okay. So here you can say the major losses. The first one is the copper losses. Okay. So these are nothing but you can also say that I square R losses. Okay, this is generally in case of in transformer windings. We are getting the losses, copper losses in transformer windings. In the winding, the current is flowing. Due to that, I square R losses we are getting. So second one, iron losses. Iron losses. Where is the iron we have? In transformer core. In transformer core. Transformer core is made with silicon steel. Steel is nothing but carbon plus copper. Sorry, carbon plus iron. Okay, so that is main ingredient is iron. So we can simply call this iron losses are nothing but transformer core losses. Okay, the transformer due to core we are getting the losses. So we can also call them as core losses. Okay, so we have some minor losses are also there, but generally we may neglect these minor losses. Okay, these minor losses are nothing but stray load losses, that is due to some of the copper parts, so and iron parts. Okay, so whenever the part is a solid in the nature, so we may get circulating currents, stray currents. Due to that, we are getting the losses. Those are nothing but stray load losses. To avoid this one, generally we go with stranded type of conductor. Stranded conductor. Okay, stranded conductors to reduce this losses. Use to reduce. Okay, apart from this stray load losses, we have one more loss that is important for exam point of view, that is dielectric loss. Dielectric loss. Okay, that is due to in case of in insulating material. Due to insulating material. If it is a perfect insulator, we may not get the losses. But if it is a practically, we may not have perfect insulator. So due to that also we may get some losses. Okay. Now we are going to discuss each and every one. First of all, copper losses. You know very well about the copper losses. So very simple points, and we may have one important question in this. Okay. So we will discuss that one. So you have to do, you have to concentrate. Just if you concentrate and if you listen, no need to prepare again. Okay, just to you, if you revise, then you will get. Okay. So total copper losses. Total copper losses in case of transformer. So the total losses, if the due to the I1 current, we will get I1 square R1 losses. Due to the I2 current, we will get I2 square R2 losses. Okay. If you transfer the resistance from secondary to primary, it will becomes R2 dash. That is, we can call this one. Sorry, R2 will comes to into the primary, and R. If you transfer R1 to the secondary, R1 to the secondary, it may becomes R1 dash like that. Okay, so it will becomes R01. It is considered as R02. So that is a total resistance belongs to primary, or total resistance belongs to secondary. Okay, so in that case, you can say the total copper losses with respect to, if you can consider I1, okay, then corresponding resistance is R01. That is equal to I2 square R02. I2 square R02. Okay, so this is considering the total resistance. Considering the total resistance. Okay, that means from this one, you can also say that full load copper losses is equal to I square R01, that is equal to I2 square R02. Okay, I2 square R0. So finally, what you can say from this one? The copper loss is proportional to square of the current. So copper losses. Let us take PCU. Copper losses is proportional to the current square. Proportional to the current square. Okay. So we know very well, as the load varies, current is varies now. As the load varies, current is varies. So no, we know very well, as load changes, current changes. Okay. As the current changes, then copper losses are changes now. I square R. Okay, as the load changes, current changes, in the sense, as current changes, copper losses are changes. Correct? Copper losses are changes. So these are changes. So that means these are variables. So called as variable losses. Called as variable losses. Okay, so as the load varies, the current varies, so I square R losses are varies, so that's why copper losses are considered as variable losses. Very important question. Okay, so for example, if you can consider copper losses at half of the load, at half of the full load. So in case of half of the load, in case of half of the full load, what will becomes the current? Current will becomes half now. At full load, the current is I. At half of the load, current will becomes half. Correct? So in place of I am substituting I by 2 whole square. Correct? So the current will becomes half. So I am substituting the place of I square by 2. So at the half of the load, what you will get? 1 by 4 times of I square R. 1 by 4 times of the I square R. Okay. So that means we can say 1 by 4 times of the I square R is the full load copper losses. Full load copper. Okay. So that means if the load is half of full load, half of the full load, the copper losses will becomes 1 by 2 square, that is equal to 1 by 4 times. Correct? 1 by 4 times. Let us take it is a x. It is the x. Here x square. We are getting the x square. So what will be the formula? Copper losses at x of full load. X of full load is equal to x square times of the full load copper losses. of the full load copper losses. All of you getting why we use always x square formula here? Because the current formula, that is the loss formula, is I square R. Current is square times. Okay. So if we half of the load, current will become half, means I by 2. So that is 1 by 4 of the full load copper losses. Okay. So if they are asking copper losses at 1 by 4 of the full load, then what will be the answer? 1 by 4 whole square into full load copper losses. Full load copper losses. Okay. Full load copper losses. All of you clear? It is a very important thing, guys. Very important thing. For example, a small question: if copper loss at full load is 1000 watt, okay, then copper loss at half of the load is dash. Okay, so many students will give the answer if the full load is 1000, half load means 500. That is wrong. Okay, what is the formula we have? Copper loss at x of full load is equal to x square times into full load copper loss. So x here is, they are asking at which of the load? Half of the load. So here 1 by 2 whole square into full load copper loss 1000. That is 1 by 4 into 1000, that is 250 watts. So as the load current decreases, the losses will be decreases a lot. Okay. If it is 1 by 2 times decreases, it will becomes 1 by 4 times. 1 by 4 times. All of you clear? Now coming to the next one, iron losses. Iron losses. These are also called as core loss. And here these losses are also called as fixed loss. Okay, fixed losses or constant losses. Constant losses. Copper losses are variable losses, but iron losses are also considered as the constant losses. Why? Because they may not depend upon the load. They may not depend upon the load. Okay. So these iron losses, we know very well, hysteresis and eddy current losses. Hysteresis loss and the second one, eddy current loss. Okay. So in the examination, at least one bit from these losses, iron losses. Okay. We can expect at least one bit from these losses. Maybe 2 bits also. Okay. That much of important. So all of you listen carefully. Okay. Coming to the first one, hysteresis loss. What are these hysteresis loss? Hysteresis loss. If you open the textbook, it is very difficult to understand about the hysteresis losses. But a simple idea is, if we have alternating current, generally in the transformer we are giving the alternating current, correct? So for positive it will be magnetization. The core will be magnetization. For negative it will be again demagnetization. Again magnetization and demagnetization. That means due to reversal of this magnetization and demagnetization, we may have some losses. Those losses are nothing but we can say hysteresis losses. Okay. Due to reversal of magnetization in the transformer core. Okay. Due to reversal of magnetization. Reversal of magnetization means half cycle is magnetization, half cycle is demagnetization. Due to this reversal of magnetization in the transformer core, we may have the losses. Those losses are nothing but we can say hysteresis losses. Okay. So note down the point. Due to reversal of magnetization in transformer core, and whenever it is subjected to alternating current, whenever it is subjected to alternating nature of magnetization force. Alternating nature of magnetization force. Okay, so for every half cycle it is a reversal, magnetization to demagnetization, demagnetization to magnetization. So note down that point. For every half cycle the magnetic domains directions changes. Okay, so the power consumed by these magnetic domains to change their orientation of every cycle is nothing but you can say hysteresis losses. Okay, changes. So the power consumed by the magnetic domains to change their orientation, after every half cycle. Half cycle is called hysteresis loss. Hysteresis loss. Okay, hysteresis loss. How it will be like? If you take the curve, we can get idea how we are getting that losses. Okay, so let us take flux density and magnetizing current. Okay, so first of all, let us take positive current. It will be a magnetizing, but the demagnetization is not like same in the back. Instead of the same path, the demagnetization is like this. The demagnetization is like this. Okay, that means here we have the loop. There is a loop is formed. Okay, this loop is nothing but hysteresis loop. Okay, so they are forming hysteresis loop. Okay, if the loop is very big, then losses are very high. So here maximum case can get H max. Okay, H max here minus H max. So due to magnetizing and demagnetizing process, some losses occur. Those losses are hysteresis loss. Okay, and the hysteresis loss formula is very important, guys. WH is considering as hysteresis loss, okay, that is equal to zeta into B max power x F into V. Okay, B max power x into F into V. So here zeta is a hysteresis constant or Steinmetz constant or Steinmetz coefficient. Okay, and F is the frequency. V is the volume of core. Okay, so if the volume of the core is less, hysteresis losses are also less. And what is this X? X is considered as hysteresis coefficient. Okay, its value generally varies from 1.5 to 2.5. So for silicon steel, it is 1.6. That means very less. Okay, so hysteresis loss will becomes also very less. Okay, this X value for silicon steel is 1.6. So hysteresis loss is proportional to B max power X into F into V. F into V. Okay, so in this hysteresis loop, height is determined by B max. Height is determined by B max, and the width is determined by volume of the core. Okay, volume of the core, and number of loops are determined by supply frequencies. If the supply frequency is having harmonics, then we will get number of loops as per their frequencies. Okay, so sometimes there is a chance to get a question on this one also. Height is determined by this height side we have B max is there. Okay, and width is determined by volume of the core. The more volume we have, more width we will get. Okay, now we are going to some research on this hysteresis formula, some operations on this formula. That is very important for exam. Okay, so let us take during operation of the transformer. What will happen during operation of transformer? This session may be somewhat of lengthy. Be patient. Okay, then only you will get a full thing. So we know the formula WH is equal to zeta into B max power X F into V. Correct. In the previous session, we have already discussed that B max always proportional to V by F. Now, we have already discussed or not? Okay. So let us take here case 1. In case of case 1. Case 1, I am taking V by F is constant. If the V by F is constant, we know very well B max is equal to constant. If the B max is constant, then WH is proportional to zeta constant, B max is constant, and once the transformer is designed, then volume also constant. So the only thing is nothing but frequency. So WH is proportional to frequency. If you remove the proportionality constant, WH is equal to AF you will get. AF you will get. Okay. Let us take one example they have given. So in the first case, they will give, if it is a 200 volts transformer, 50 hertz supply, then we have hysteresis losses are 100 watt. If you change the supply, to 160 volts and the frequency is 40 hertz, then what will be the hysteresis loss? Then what will be the hysteresis losses? Here, whenever they have given the question like this, by changing the voltage and frequencies, first step what you have to do, we have to check V by F is constant or not. V by F is constant or not. So that is V1 by F1 is equal to V2 by F2 or not. We need to check this one. Okay, let us take V1 by F1, 200 by 50. V2 by F2, 160 by 40. 50 ones, 54, 4 ones, 4 4. So V by F is constant. So V by F is equal to constant. If V by F is constant, then what is the case we have? WH is proportional to frequency. WH is proportional to frequency. So here frequency is reduces 50 to 40. Then what about the hysteresis losses? Those are also reduces in the same proportionality. That is 100 to 80. Okay, so then in this case WH2 by WH1 is equal to F2 by F1. From this, WH2 is equal to WH1 into F2 by F1, that is F2 is 40, F1 is 50. So you will get WH2 is equal to 80 watts. So like that you can easily get. Here just for understanding I am giving all this. In the examination no need to do all this. Okay. So in your mind itself 200 by 50 4, 160 by 44. So it is a balance. It is the V by F is constant. Then WH is proportional to just frequency. As frequency is reduces means hysteresis losses also reduces. Okay. 50 to 40 means 100 to 80. Okay. So within 10 seconds you can give the answer. Okay. Let us take the case 2. Let us take the case 2. If V by F is not constant, these are very important guys. Not constant in the sense B max is not constant. Okay, then what about the hysteresis losses? Proportional to zeta is always constant. B max power x. B max power x. Okay, and we have the frequency. Value is the constant. Let us take B max is considered as B max is proportional to B by F means V power x by F power x into F. Okay, so that means here you will get V power x F power 1 minus x. 1 minus x. Okay, let us take if the x is 1.6, then hysteresis loss is proportional to V power 1.6 into F power 1 minus 1.6 means minus 0.6. Minus 0.6. Okay. So from this one, what you can say? WH is equal to V power 1.6 by F power 0.6, and we have to take one constant, that is nothing but A. That is nothing but A. So A V power 1.6 by F power 0.6. From this one, hysteresis losses is inversely proportional to frequency. Inversely proportional to frequency. So if it is not a constant, V by F is not a constant, WH is inversely proportional to frequency. Okay. Frequency. Let us take one example on this. Let us take one example on this. If you apply 200 volts, 50 Hz, your hysteresis losses are 100 watt. Okay, if you change your supply like 160 volt, 30 Hz, then what will be your hysteresis losses? If they have given the options like option A is 100 watt, option B is 50 watt, option C is 150 watt, option D is 0. So if they have given like this, okay, so here what you can idea, 200 by 50 means 4, here 160 by 30 means is nothing but 5 point something. So V by F is not constant, is not at all constant. Then WH is proportional to V power 1.6 by F power 0.6. F power 0.6. Okay. So from this one, we can take that WH2 by WH2 H1 is equal to V2 by V1 power 1.6. Okay, 1.6 by F2 by F1 into power 0.6. Okay, so from this one, if you go with the solution, you will get WH2 is equal to 92.3 watts. 92.3 watts. Okay, so a simple idea, as the frequency is decreases, okay, as the frequency is decreases, generally what we can say, sorry, here it is have taken somewhat of wrong. So V power 1.6 only. Okay, frequency is decreases, but voltage also decreases. So both are decreases in the sense here voltage is 1.6 times. So it is the more domination. As the voltage decreases with respect to frequency, hysteresis losses also will be decreases. So that's why it will becomes generally less than 100. Okay, less than 100. But they have not given the option. Okay, let us take option D as 92.3 watts. Okay, so then you will get the answer as option D. Okay, so like that you can calculate, but no need of worry, they may not give this type of example, especially the maximum they will give case 1 type. Okay, why? Because calculation is somewhat of difficult here. Okay, so all of you clear now? So all of you clear? So finally what you can say, case 1, as V by F is constant, you got WH is proportional to frequency. If the V by F is not constant, this WH is proportional to V power 1.6 by F power 0.6 or V power 1.6 into F power minus 0.6. Okay, so all of you clear, I think. Now coming to the next one. Next iron losses. What is the second iron losses? Eddy current losses. Very important. Eddy current losses. So what are these eddy current? Eddy currents are nothing but you can say circulating currents. Eddy currents are nothing but you can say circulating currents. Okay, for example, if the conductor is this much of area, okay, whenever the area is very less, then the currents may not circulate within this conductor, so the eddy current losses will be less. Whenever the area of the conductor is more, this much of area we have, whenever the area of the conductor is more, then there is a chance of circulating currents. The currents may be rotate within the conductor itself. For example, road is a just a 5 feet road. Okay, then if for example, let us take a 7 feet or 8 feet road. Okay, if the car wants to rotate, the car may not rotate, may not circulate within that road. Correct. Whenever the road is, for example, a 20 feet road, in that 20 feet road there is a chance of circulating. Okay, for example 25 or 30 feet road, then car can be circulate. Here also same, whenever the area is less, the current may not circulate. If you send here, you can get, it will be reached to here. Okay, so whenever the area is more, there is a chance of circulation. Okay, so this eddy current losses are occurs whenever the core of the transformer area, cross section area is more, then eddy current losses will be more. Eddy current losses will be more. So to reduce the eddy currents, what we have to do? We have to reduce the area of the conductor, area of the core. Okay. So if area of core is reduces, simply eddy currents are less, so we can get less eddy current losses. So how we can reduce the area of the core? By laminations. By laminations. Laminations in the sense we can cut the large cross section area of the core into small parts like a book. For example, if you can consider it is a one full core. Here if you have this much of area, then there is a circulation current, circulating currents within itself. Okay, so to avoid that one, what we are doing, we are laminating like this. Okay, that means we are taking a small cross sectional area of the core. So that means each paper is like a one core. Between the two cores we have some insulation. Okay, some laminated with any paint laminated, okay, or vanishes like that. Okay, so and we are bunching all them together to get a high mechanical strength. If we can take a single core, that means single paper, we can easily break that one. But if you can consider it, we are bunching all them together, and if you want to break, then it is difficult. It increases its mechanical strength. So to get that high mechanical strength, we are bunching all the cores into a single core. Okay, so then the total core area is somewhat of high, but individual area of the core is less, so eddy currents we can say less. Correct? So all of you clear? So whenever the currents more, eddy currents more, higher the eddy current losses. So if you want to reduce the current, if we can reduce the conductivity, if you reduce the conductivity of that material, then also eddy current will become less. So the possibilities are reducing the conductivity and by laminations. Okay, so note down, eddy currents are nothing but circulating currents within the core. Currents within the core. Okay, why? Because in the core, because core material generally made with silicon steel, that is steel also having some conductivity, because core material has some conductivity. Okay, some conductivity. Due to this circulating current, circulating currents, we may get losses. Okay, we may get losses. These are nothing but eddy current losses. Eddy current losses. These eddy current losses generally proportional to its conductivity. Proportional to conductivity. If the conductivity is less, eddy current losses will become less. Okay, so how to reduce this eddy current losses? To reduce these eddy current losses by adding 4 to 5% silicon to steel, then conductivity of core reduces. As the conductivity of core reduces, eddy current losses reduces. eddy current losses reduces. Okay. And the second thing is the main thing, by using lamination. Laminations of transformer core. Okay. So due to this, what will happen? We are reducing the area. So due to this, area of cross section of core or cross section of core reduces. Okay. As area of cross section core is reduces, we know very well resistance are proportional to L by A. As the area is reduces, resistance is more. So as resistance is more, then eddy currents are less. Okay, the current, circulating currents will be reduces. As the resistance is more, current is less. So then eddy current losses will be reduces. Losses reduces. Okay, so the very important method is nothing but laminated the core. Okay. All of you clear? Yes. Now coming to the formula of this eddy current loss. Okay, eddy current loss formula. WE is nothing but K into B max square, F square and T square. Okay, B max square, F square and T square. We know very well F is the thickness of lamination. Sorry, T is the thickness of lamination. Okay, if thickness is less, eddy current losses will be less. Okay, frequency is a frequency of some. Okay, B max you know very well, maximum flux density. K is a constant. Okay, so here let us take case 1. Same like previous. If V by F is equal to constant, then B max is constant now. If you are not getting, no need of worry. Watch second time, then you will get idea. Okay, it is a very easy thing. But if you are first time watching the transformer in depth, then try to watch again. Okay. So now W is proportional to K is a constant, B max is a constant, and once the machine is designed, T is the constant. Thickness of lamination is constant. So proportional to frequency square. That means WE is equal to AF square. Okay, so A already we have taken in the hysteresis losses na, so it is better to take another constant, that is B, BF square. Okay, let us take a case 2. If the V by F is not a constant, then B max is not a constant. In that case, what you will get? W is proportional to K is a constant. B max, B square by F square. It is not constant now. So into F square. T is a constant. Thickness of lamination is constant. So F square is cancelled out. W is proportional to voltage square. So that means WE is equal to BV square. BV square. So from this one, whenever there is a V by F is not constant, it is not depending on eddy current losses, not depends on frequency here. Okay, not depends on frequency here. Okay, all of you clear? All of you clear? So I want to summarize. Okay, so what is the summarize? I have taken case 1. Okay, what is the summarization I have done? Case 1. That is, let us take a condition. Condition. What is the condition? V by F is equal to constant. That is, B max is equal to constant. Okay. In this case, what about the hysteresis losses? Hysteresis losses. We know hysteresis losses is equal to, let us take this one at the top. We know hysteresis loss is equal to zeta D max power X F into V. Okay, F into V. So here if the B max is constant, then you will get WH is proportional to F. Correct? Okay, that means WH is equal to A. Here eddy current losses. K B max square F square T square. Here V by F is constant, that is B max is constant, then what you will get? F square, that is WE is equal to BF square. BF square. So then what about the total losses in this case? AF plus BF square. Okay, AF plus BF square. If I take all these in the same, then it will be very easy. I think don't mind, I have wasted your time. So eddy current losses K B max square F square T square. So let us take total losses. Total iron loss. Okay, the B max is constant. Eddy current loss is proportional to F square BF square. So then total losses is equal to hysteresis plus eddy current AF plus BF square. So it is the relation for the total iron losses whenever the B max is constant. The second case, V by F is not constant. So then V max is not constant. Then what about the hysteresis losses? Hysteresis losses not constant means V power X by F power X. Let us take X as 1.6. Then you will get B power, B means V by F. So V power 1.6 by F power 1.6 and F power 1. So that is, you will get F power minus 0.6. So F power 0.6 you will get. Okay. 0.6 you will get. And what about here? If the B max is not constant, V square by F square, F square cancelled out, we will get proportional to V square. So WH is equal to A V power 1.6 F power minus 0.6. Here WE is equal to BV square. So finally what you will get the total losses? Here A V power 1.6 F power minus 0.6 plus BV square. These are the total iron losses. Okay, let us take some other operations. Okay, by if the V1, sorry, voltage is constant, frequency is decreases. Okay, voltage is constant, then frequency is decreases. Then what happened to the hysteresis losses? One is constant, one is varying, means the second case only, correct? In the second case, here V is a constant they have given, A is also constant, so WH is proportional to F power minus 0.6, that is F power 0.6. So as frequency decreases, hysteresis losses will be increases. And what about here? As the voltage is constant, eddy current losses will be dependent on only voltage. As voltage is constant, WE is constant. These are constant. Eddy current losses will be constant. Then what about the total losses? One is increases, one is constant, means total losses will be increases only. Total losses will be increases only, correct? Then fourth case, if the voltage is decreases and frequency is equal to constant. If in this formula, if the frequency is constant, then hysteresis loss is proportional to V power 1.6. As the voltage decreases, hysteresis losses will be decreases. Okay. And what about the eddy current losses? Proportional to V square. As the voltage decreases, eddy current losses decreases a lot. So the total losses will be decreases. Total losses will be decreases. Okay. All of you clear? So these are the very important operations on the iron losses. Okay. Very important iron losses. Okay. All of you clear, I think? Okay, all of you clear? And in the same way, in the eddy current losses, K B max square, F square, T square. So WE is proportional to thickness of lamination square. Thickness of lamination square. Okay. If you go with less thickness, that means if you go with very thin, then eddy current losses will be less. Okay, if the thickness is 0.35, then eddy current losses will be less. If the thickness is 0.5, somewhat of eddy current losses will be more. Okay, somewhat of eddy current losses will be more. Okay, so like that we can get the idea. Like that we can get the idea. Okay. So if you consider B max and K is constant, W is proportional to F square T square. If you reduce the thickness of lamination, you can go with the high frequency. We can go with the high frequency. Okay, you have to go with the high frequency. Then also you will get the same losses. Okay, if you want to reduce the frequency, you need to go with the high thickness also. Okay, that means if you have a 50 Hz frequency of the transformer, then you can go with the 0.5 mm of thickness. Okay, if you go with some high frequency, generally as the frequency is more, then eddy current losses will be more. So to get the same eddy current losses, what you need to do? If you increase the frequency in the same way, you have to decrease the thickness. So you need to decrease the thickness like this. Then W will be almost same. Okay, to get the same eddy current losses, if you are going to increase the frequency, you need to reduce the thickness as well. Reduce the thickness of laminations as well. Okay, then you will get the same eddy current losses. Okay. So finally, what you can write? High frequency transformers are designed with a less thickness of lamination. Designed with less thickness means thin lamination. Thin laminations. Okay. Whenever the laminations are thin, that is the area for this insulating material is less. So that means stacking factor Ks is equal to somewhat of less. So the stacking factor must be less. Okay. You know very well Ks is equal to always A net by A gross. So if you go with the thin laminations, your gross area is maybe somewhat of equal to net area. Okay, somewhat of net area. Okay, so if you go with the thin laminations, the gross area is reduced, so stacking factor we can improve. That means whenever the high frequency transformer, here it is better to take here high frequency transformer are designed with thin laminations. Okay, so take this one. Forget about the stacking factor here. Okay. All of you clear up to this? Okay, now coming to the next one, minor losses. In the minor losses, we are going to discuss dielectric losses. Dielectric losses. So the loss due to dielectric. Okay, so note down dielectric loss normally takes place in insulating material. Normally takes place in insulating materials. Insulating materials of transfer. Sometimes this pen tab is not at all working, so some letters may not visible. Okay, so dielectric loss normally takes place in insulating material of transformer, such as any solid or liquid insulations. Okay, so if you can consider pure dielectric material, in this case, no dielectric loss. Why? Because here, if you can consider in case of pure dielectric, the impressed voltage and displacement current angle is 90 degrees. Okay, the angle between these two is 90 degrees. So there is no active power. The active power due to this is zero. So there is no dielectric loss. Okay, there is no dielectric loss. In this case, active power does not exist. But in case of practical dielectric, in case of practical dielectric, what will happen in the sense, if you apply the impressed voltage, the current may not 90 degrees with the impressed voltage. Okay, so we may have some angle, I displacement. That means you may have the delta between previous I to present I. Okay, so you may have the delta. If the delta is more, then current will be, direction will be towards like this. Then the angle between the voltage and current is reduces. As the angle between the voltage and current reduces, cos phi is increases. So that means active power will be increases. Okay, so as delta is increases, that means sine delta is increases. As sine delta increases means dielectric loss increases. Why? Because the dielectric loss generally proportional to sine delta. Okay, so generally the dielectric loss formula, V impress I displacement into sine delta. Okay, as sine delta is more, dielectric loss will be more. Dielectric loss will be more. So finally, we can say the dielectric loss proportional to sine delta. Sine delta is generally proportional to delta. Okay. Okay. So that means dielectric loss generally dependent on this impressed voltage. Okay, and the car displacement current and the angle. Okay, so it is this angle is not dependent on the load current, so that's why it is considered as generally constant losses. Okay, so these losses are generally, you can say, somewhat of constant losses, somewhat of constant losses. Okay. Okay, students, I want to summarize all this. So we have hysteresis and eddy current losses. And in this, so many students having confusing the formulas. Correct? Hysteresis formula, eddy current losses formula. So I have a small trick to remember in this eddy. D into D square is there. Correct? So in the formula also we have square in terms. Okay, all are in the square. K, B max square, F square, T square. Okay, so in the D into D square. So all the terms are in the square format. That is the easy way to remember. Correct? In the hysteresis losses, zeta into B max power X F into V. If you have the X, okay, then here single terms only, F and V only. V is the value, here T is the thickness of the lamination. Okay, so all of you getting? So all of you getting the trick. So by using the trick, we can easily remember the formulas. We can easily remember the formulas. If you know the formulas, we can easily get the answer for this type of any questions. Okay. Okay, students, if you like my class, don't forget to click on like option. And also, if you want PDF, you can download from sunelengineeringacademy.com. Okay, so try to download 6 subjects electrical engineering PDF. Okay, so if you open sunelengineeringacademy.com, then you will get a first video that has 1 minute duration. So if you watch that one, then you will get the idea how to download. Okay, just wait, I'm showing. Yes, here you have how to download the PDF. The first video is there now, how to download the PDF. Okay, if you click on that one, 1 minute video and watch that, you will get the idea. Okay, and here in the under RRB JE or SSC JE electrical engineering, you have the first PDF itself, electrical 6 subjects PDF. Okay, so if you want only the machines notes, you can go with the machines. If you want only the transformer, you can click on the transformer. Okay, so and add the PDFs whatever you want to the cart and check out, and finally if you click on my account and click on downloads, you will get the PDF. Okay, so don't forget, before going to buy, watch this 1 minute video how to download the PDF. Okay. Okay, students, I'm going to end the session. All of you, thank you so much for watching. Take care. Bye, guys.